Huh. Just about 6 seconds. Hi, Mr. Clark. This is Jeremiah. I'm explaining to you now how our roller coaster works. Okay? So, up here at the top left corner is the max potential energy. That is where the marble has the most potential energy because it is the highest point on the roller coaster. Over down here we have a bunch of different tags. Right here I labeled this the max kinetic energy because this is the fastest that the marble goes according to my calculations. I would have put it down here, but I really don't think it's there. Now this is where the velocity decreases and the work net is negative because this is where the ball stops. And according to my ancient physics tome that I got at the beginning of the year, when things are stopping, that's when the net work is negative. This is also the place where the max velocity is, funny enough. Well, the max velocity is up here, but they're on the same side, it's fine. I also put projectile motion there because projectile motion, well, it's happening everywhere, but this is the only place where the marble is kind of a free body. It's not attached to one of these coin wrappers. My mom had hundreds of these coin wrappers, and she's just been like saving them for years, and now I get to use all of them to build this roller coaster for my favorite teacher. How great. Anyway, it's the only time that the marble isn't touching one of the coin wrappers. It drops it down here, and I labeled that projectile motion. Now this is interesting. This is centripetal force and centripetal acceleration. I would have put these on my corners, but my corners aren't very round, as you can see. My corners are pretty square. In fact, this one's a literal square, has a square right on it. Let me show you a different one. This one, it's not very round. It's a direct 90-degree angle curve. Not curve, just 90-degree angle. So I figured I'd put it inside of this tube because technically, whenever let me get this marble out. Whenever the ball does fall into the tube, it does roll around a bit, and so I figured that it would have centripetal force. Okay, let's go through it as if we were the marble. That's a good idea. Oh yeah. Okay, this is the max potential energy. We go down. Okay, here we see Newton's first law of motion. An object in rest stays in rest, and an object in motion stays in motion. Here, unless acted upon by another force. Now, I was wondering where to put this one. It was kind of tough. I figured I'd put it here because this one, because you can see that the angle changes down here, and when the angle changes, the force of gravity actually, well, the force doesn't change, but the acceleration on the ball changes. And so the ball actually does slow down a little bit because of friction and because of the acceleration changing. And that was a good example of Newton's first law in place because the speed changes around this point because the angle changes. Newton's second law and third law are down here because Newton's second law is that, oh geez, Newton's second law is that force equals mass times acceleration. Newton's third law is down here because you see these sticks here. This is a troubleshooting thing. If I take these out, can I even take these out? If I take these out, you'll see that this coin thing actually moves a little bit. And I had to put those sticks in there so that it wouldn't move around a bit. But it shows Newton's third law is that every action has an equal and opposite reaction. So that was, let me try that again. You can see it shake a little bit whenever I drop it in. Where did that darn marble go? Anyway, and of course we have work net is positive right here because, well, work net is positive. Work net is positive in most of these places. I just figured I'd put it here because this place was looking a little lonely. I thought it wanted a bit more signs. WorkNet is positive here because the velocity is, because the distance is increasing. And so the network, let me check myself. Let me see if that's right. I believe that's right. But belief is not what makes science. WorkNet positive. Okay. For our final ones, we go blue. Oh, I see the marble in there now. Okay. Now we have work due to gravity right here. All work is due to gravity in this contraption because I am not touching it at all, and there's no mechanical energy being put into it, and there's no electrical energy, so it's all gravity. Maybe a little friction, but mostly gravity. And gravity is 10 meters per second per second. And, so acceleration equals 10 meters per second per second. Now, the velocity is increasing because it's pointed downwards at an angle that's different from this angle. It curves downwards, which means the velocity is increasing, which means also that velocity is increasing because it's acceleration, because the acceleration is 10 meters per second per second. And because the velocity is increasing, the kinetic energy is increasing. I'll show you that right here. If velocity goes up, then mass times velocity squared over 2, which is our kinetic energy formula. It'll also go up. We also have the conservation of energy right here, because as you can see, as the kinetic energy increases, the height decreases. Because the height is decreasing, that means that the potential energy is decreasing. So as kinetic energy increases, potential energy decreases. That's all for our project. I'll send you the day notes and the complete overview as a separate file. Thank you, Mr. Clark, for giving us a second chance. I promise next quarter will be a lot better. I love you. Have a great spring break. Don't get sick. Goodbye.